And I would like to continue the discussion of free fermions in 3 dimensions. That's what I was looking for. And let me just put on the blackboard a few equations we had yesterday. So we used real gamma matrices, wrote the Lagrangian I with background field A, and we had gamma matrices, and we wrote how C and T act. That's important for us. So C of psi is psi dagger. Both are column vector. Dagger for me is a column vector. And T of A was minus A. And C of A is minus A also. But that's viewed as a differential form, which means that the zeroth component is even, and the time component is even, and the spatial components are odd. This guarantees that electric charge is time reversal even. We also discussed T on the fermion, which was gamma 0 psi. And that means that if I write psi as psi 1 plus I psi 2, since T is anti-unitary, psi 1 and psi 2 transform under T with opposite sign. If you don't like that, you can combine and have CT. And in CT, if we take CT as the basic thing, then charge is not CT invariant. It's odd under CT. And then psi 1 and psi 2 transform with the same sign. And we had 2 conventions, my conventions and Talia's convention. And both are equally valid, and we should learn to work with both of them. And I even emphasized in the first talk, and I think to some extent even last talk, the duality exchanges my conventions with her convention. So neither is more fundamental than the other, although one of them might be more convenient than the other, and maybe later in this talk or in the next talk we'll see how this comes to be quite significant. And these objects satisfy T square is minus 1 to the F, and C square is 1, and C and T commute, which you can check for yourself. We also discussed the mass term. So first we impose the U1 symmetry. So the mass term is that. You can check that it's real. My gamma matrices are real. And it can be written in terms of the Majorana components as I M psi 1 bar psi 1 plus psi bar 2 psi 2. This is invariant both under the U1 and under charge conjugation. Charge conjugation, if you just look at this formula, it flips the sign of psi 2, but does not change the sign of psi 1. So psi 2 picks a minus sign. This doesn't have psi 2. Here we have twice the minus sign, so it's C invariant. But it's not T invariant. So the U1 is okay, and C is okay, but T is broken. And I ask you, what about CT? Is CT preserved or broken? Broken. So CT is also broken. Well, it's enough to say that. It follows from it. So this is where we ended last time, and I'm continuing to analyze the classical theory, and then we'll discuss the quantum theory. So imagine we want to break the U1. Say U1 is broken. So there's a subgroup of the U1, which is Z2, which we can think of as minus 1 to the fermion number, which acts as a minus sign on psi. So the fermion is fermion number odd. Now, why do we want to preserve this symmetry? What's wrong with breaking this symmetry? There's something sacred about this symmetry. Sorry? I can't hear you. Well, it's true that T square is minus 1 to the F, but there's something more sacred about it. It's part of the Lorentz group. So minus 1 to the F is part of the Lorentz group, so we should better not break it. That was not the case in the quantum mechanical example, where it was just any random internal symmetry. Here it's not. So we are not going to break this. So we could break U1 to minus 1 to the F. And since psi has charge 1 under the U1, then psi dagger is invariant. But if we're willing to break the U1 symmetry, we can write an operator of charge 2 and an operator with charge -2. So altogether, there's a two-dimensional space of mass terms that we can write down, and we can take as basis for them I psi bar 1 psi 1 minus psi bar 2 psi 2, or we could take I psi bar 1 psi 2, which happens to be the same as psi bar 2 psi 1. You can check that they're equal. There was a question here.
Yeah. You can just explain.
Sorry?
How much part of the Lorentz group?
Because if you start from ordinary rotations, so forget even the signature and all that, so we have an SOD symmetry. So this is part of the Lorentz group, but when we introduce spinors, they are not in representations of SON. We have to go to a double cover of SON, which is usually denoted by spin n, and a transformation of 2 pi rotation, which is trivial in SON. It's non-trivial in spin n, and it acts as -1 on all the fermions. And it acts as -1 to the f. So in theories without spinors, the group that acts is SON, and we don't need to worry about -1 to the f. In problems with spinors, we have to think about spin n, and then -1 to the f is part of the Lorentz group. So we have really 3 linearly independent mass terms that we can discuss. This direction is preferred because it preserves the U1. But if we don't want to preserve the U1, we can turn on either this or that. Without loss of generality, I can limit myself to one of them. Why is that? Why is it that without loss of generality, I can pick one and not the other, or any linear combination of them? As I said, together, they form an operator of charge 2. This is an operator of charge 1, or charge 0, so it's invariant under the U1. These carry charge 2. Indeed, it breaks the U1 to Z2. And therefore, by performing a U1 transformation, these two guys form a vector, and I can always pick a basis where I pick only one of them. So what I'm going to do now is pick the first one. I'm going to talk about this one. So imagine we have a Lagrangian, that this guy is absent, and this is absent, and this is present. Based on what I said so far, this is exactly the same as saying that this is absent, but this is present. But the words would look a little bit different. So what I'm going to do, I'm going to discuss the Lagrangian with only this term, and I leave it as an exercise for you to derive the same physics when only this term is present. It's not completely obvious, but you'll see what you could do. So what are the symmetries? So we have a Lagrangian which has only this mass term. It's real and it's valid mass term. So U1, we've already said, is broken to Z2, which is -1 to the f. We still have this C and T. What happens to C and T? C, we've already said, it maps psi 2 to minus psi 2. So that's still a symmetry here. All we did was to flip the sign from plus here to minus here. So that's a symmetry. The U1 is gone, but Z2 is preserved. What about T? T, we said before that this is T odd. And you can check that this is also T odd. In fact, you've always learned in school that in 3 dimensions, if you turn on a mass term, it breaks time reversal. However, this is a little bit too fast. It's too fast because we broke the U1 and we broke T. We preserved C. Can we form a combination of them which is unbroken? So I claim that T prime, which is T e to the I pi over 2 Q, is a symmetry. So that's an operation, first of all. It's anti-unitary because this is unitary and this is anti-unitary. So this is an anti-unitary transformation. It commutes correctly with the Lorentz group, because this part commutes with the Lorentz group, and this one has certain commutation relations with the Lorentz group. So T prime also maps time to minus time. And this part, this is broken by the interaction, and this is broken by the interaction, but the combination is unbroken. So this Lagrangian, despite appearance, is actually time reversal invariant. It's invariant under this particular time reversal transformation, and we can show explicitly what it does. T prime on psi 1 is minus gamma 0 psi 2, and T prime on psi 2 is minus gamma 0 psi 1. And you can substitute into the Lagrangian and see what happens. In other words, it acts exactly the same as T, but it exchanges psi 1 and psi 2. Since it's exchanged, this thing was T odd. So the T part is exactly the same. It maps this to itself and this to itself with a minus sign. But since I also exchange 1 and 2, I get another minus sign from here. So this system, despite appearance, is actually time reversal invariant. So what do we have? We have Z2, we have charge conjugation, and we have T prime. So we have Z2, the symmetries are minus 1 to the F. We cannot mess with that. That's part of the Lorentz group. We have C, and we have T prime. What is the algebra of these guys? So I've already used the fact that T commutes with Q, and therefore T e to the I alpha Q is e to the minus I alpha Q T, because it's anti-unitary. This was this confusing thing that if it commutes with Q, but this is the funny thing about anti-unitary transformations. If it commutes with Q, it does not commute with the group element. If it commutes with the group element, it does not commute with Q. So Talia's T, for instance, does not commute with Q, but it commutes with the group element. And my T that commutes with Q, but does not commute with the group element. So we can use that in this description of T prime and derive that T prime square is minus 1 to the F. That's good. That's how we normally expect time reversal to act. So far so good. Not only is T prime anti-unitary and has the proper transformations with the Lorentz group, it also lifts to what is known as spin plus. It lifts correctly to what we normally expect in physics. So that's good. However, there's a little bit of a surprise. So C square is 1, the same way it was before. But Ct prime, which deserves to be called Talia's T, is actually plus 1, not the same as minus 1 to the F. And related to that is that C and T commuted before. Where did I write it? Here. C and T commuted before, but now I'll try to squeeze in here. Can you see here at the bottom? So Ct prime is T prime C times minus 1 to the F. That's surprising. The first surprise was that this system has time reversal symmetry. And the second surprise is something we are not familiar with. It's not very common. Some of us are not familiar with. That this time reversal symmetry does not commute with charge conjugation. So on bosons, there is nothing subtle. On bosons, this is 1. So all these subtleties don't exist with bosons. But the algebra of time reversal with charge conjugation is not the standard one. So if you're only interested in time reversal, you don't care about C, nothing new. But if you have also C, then it does not commute with T prime.
But it anti-commutes, right?
Well, it anti-commutes on fermions and it commutes on bosons. Yeah. So you can't say, it's anti-commute because the algebra is extended by minus 1 to the F. So as long as you have only bosons, the symmetry is SON, and then none of these issues arise. But if you lift SON to spin n, then T should be lifted also. It's called pin plus n. So that's good, but if you also throw in C, it does not commute with T. That's a fact of life. So I'm leaving now an exercise for you. I emphasize that this term and that term are essentially the same, right? They're related by a choice of basis. So you should be able to derive the same result in the same algebra by analyzing the symmetry of the system that does not have the U1 invariant mass term, does not have that, but has this. And the obvious reaction would be, of course, it should work, but it's not completely trivial. And this is a nice exercise, because if you're not that fluent, not that comfortable with anti-unitary transformations, there are lots of eyes that you have to keep attention on, and you will see that this term, if we have just this term and not that one, it is actually T invariant. We don't have to modify T, but we do have to modify C. So we don't modify T, it has the naive T, but it doesn't have the naive C in such a way that the algebra is the same. More mathematically, this algebra that we have here, if we go from one picture to another, is being conjugated by a broken U1 symmetry, the U1 transformation that maps us from here to here. So I recommend that you do this exercise. I think it's extremely educational, and it's straightforward, and it must work. These are the best exercises. It must work, but it's good to really make sure it works, because it knows how it will show you that you really know how to manipulate these anti-unitary transformations. Okay, so far we discussed the classical theory. Now we graduate to the quantum theory. So we take the same Lagrangian, this one, and we want to study it quantum mechanically. There's a lot of literature on this, and surprisingly and disappointingly, it's very, very confused. And this is one of these examples that the mathematicians had it right all along. Few physicists had it right all along, but the majority of the community had it completely wrong for decades. So I'll first repeat the wrong words so that we'll know exactly what it is that, if you never heard the wrong words, don't pay attention. If you did hear the wrong words, this is exactly what you need to uproot, and we'll then plant the new seed. The words that are often said is that the functional integral of this massless fermion is not gauge invariant. That's what people often say. The functional integral is not gauge invariant. And in order to make it gauge invariant, we add by hand another term which is not gauge invariant, which is U1 level a half, made out of A. Such that the combination, the mistaken gauge invariance between the measure of the path integral and the term that we add by hand, the mistakes in both cancel each other, and that is referred to as an anomaly. I've been educated by this dogma for decades. The younger people in the audience probably either never heard it or were educated by this dogma for fewer than decades. I remember trying to convince some of the more senior members in the audience that this is actually wrong. I learned it from Witten, but it also exists in the math literature. In the math literature, it's completely common. The correct version is completely common. So I'll do it now. So we need to understand how to calculate the functional integral of psi. It existed also before this in the paper of De La Pietra, Moore, and Alvarez Gomez in the 80s, which they got it right. So we need to compute the functional integral over psi, and it should be straightforward because it's a free field theory. So what can be easier than a free field theory? So in a path integral, what we do is compute the determinant of d slash. And we might need to take a square root or in its Pfaffian and so forth. All the issues are with the plus or minus sign. But that's all. This is what the topic of the subject is. Instead, I'd like to do it in a different way that I think will be more illuminating. And then I'll do the more sophisticated way. So I'm going to put the system on S2 times R, where R is time. So imagine space is an S2, and R is time. And I put this fermion with the background field A on that system. And recall that A is a classical background field. So I can specify A to be whatever I want. And I'm going to specify A such that the integral of dA over space is 2 pi. In other words, I take S2 and I put 1 unit of magnetic flux through the sphere, and I'm just studying the quantum mechanical problem of the fermions. That's clear what I'm doing? So we need to diagonalize the Dirac operator. And the key thing about it is that it has eigenvalues. And the key thing about the eigenvalues is that they are zero modes. So there's one psi and one psi bar, zero modes. Zero modes. More generally, if we have flux m and the fermion has charge n, there are m times n zero modes. And these zero modes have zero spin. Again, intuitively, I'm trying to connect to various things that you might have heard. This is a charge 1 particle in the background of a monopole. It has its own intrinsic spin, which is a half. And the magnetic, when you take a charge 1 particle in the background of a magnetic monopole of charge 1, you get another unit of a half unit of angular momentum in the electron monopole combination. This was known to Dirac. And together, the two of them together combine to an integer spin. I got the reference wrong? Yeah.
On S2, we also have to worry about the spin connection.
So I take the standard one. Take the standard one, put an S2 here in space. And so we have psi and psi bar zero modes. They are both spinners. So we write the quantum field theory of psi becomes a quantum mechanical system of all the modes of psi. Most of the modes, an infinite number of them, are non-zero modes. So forget about them. They do what they do. We just focus on the dynamics of the zero modes. And what would be the Lagrangian of the zero modes? So let's look at the various terms. And here we could also add I k over 4 pi AdA. This is this counter term that we discussed. So actually, let's start with this term. And let me look where I'm with Lorentzian signature. So there's no I here. So the dA integrates to 2 pi. Get that? And I have it either from here or from here. So I have a term Ka0 in the Lagrangian. That's what comes from here. What do we get from here? We have one psi and one psi and one psi bar zero mode. So I have I psi bar dA psi, and this whole thing is integrated dt. This is the effective quantum mechanics of the zero mode, where this psi is only the zero mode. And this is our Lagrangian. Have we seen this Lagrangian before? Yeah, yesterday. Yesterday we analyzed this Lagrangian in a lot of detail. And what did we say? It said it has two grounds, two states. This is a two-state system. I said that today a two-state system is called qubit. So it has a qubit. This is the modern terminology. And it has two states, which have electric charge k and electric charge k plus 1. What about the symmetries of the problem? We started with something that has U1, still a symmetry of the problem. It has C, and it has T. What does this monopole background do? Does it preserve C? We specify that the integral dA is 2 pi. Does this preserve C or not? No, it does not preserve C. We have magnetic flux 1. C will convert it to another problem where the magnetic flux is -1. Does it preserve T? Does not preserve T because we said that magnetic field is T odd. But it does preserve CT. So this background preserves CT. This quantum mechanical Lagrangian has more symmetries. It has both C and T. But this is a peculiarity of the leading order term. We can discuss higher order terms that would not preserve this symmetry. And now we can just copy what we said last time. which was yesterday, we have an anomaly. It's the same anomaly we discussed yesterday, exists now in the three-dimensional problem if we compactify it on S2, if we place it on S2 with 1 unit of magnetic flux. And what are the options we have? Option 1, say, is the U1 symmetry is still there, but C and T and all that are messed up, as we discussed yesterday. Option 2, so here we can discuss only CT. It's the only symmetry that our background preserved, but now we see that it messed up. Alternatively, we could say, no, we got the normalization of A wrong. We should put a 2 here and a 2 here, and then we can choose K to be a half. And if K is a half, we can preserve the discrete symmetry, but we lose the proper periodicity of the gauge field. And what was option 3?
Adding a bulk.
Adding a bulk, very good. So we can add the bulk to this quantum mechanical system and preserve everything at the price of having the bulk and having to specify what the gauge field does in the bulk. Now we'll go back to the three-dimensional problem, and any problem we found here must exist here. There might be additional problems in this additional, more subtle things in this problem which are not present in the baby problem. But whatever disease we have here, it must also be a disease of the full system. And indeed, it is true that the full system has an anomaly, and the anomaly has exactly these 3 options. It means that we have exactly these 3 options that we have just discussed. And the analysis in the full three-dimensional problem is very similar to what we did in the quantum mechanics example yesterday. In fact, that's one of the reasons I went through this quantum mechanics in so much detail, because it exhibits all these subtleties in a setup where we could actually write down very, very explicitly in terms of elementary functions what the partition function is. So the full partition function is its absolute value. And we have this Chern-Simons term, minus I k over 4 pi integral AdA. Okay. And we also have minus I pi over 2 eta of A. And I'm suppressing the metric. There are all sorts of terms that depend on the metric that I don't write down. And as I said yesterday, this eta is 1 over pi, the integral of there's a bug in my notes. Sorry. Mod 2. So what we have here is almost like U1 level a half, but not quite. This thing is almost the same as U1 level a half, but not quite. One difference is that U1 level a half is not well defined, whereas this thing is well defined. The variation of both of them for generic A's are the same. So as far as equations of motion, they are the same. Or in other words, e to the I pi eta is e to the I over 4 pi integral AdA. So that's okay. But what we need here is the square root of this equation. And the square root of this equation is such that on the left-hand side we have a well-defined thing, and on the right-hand side we don't know how to take the square root. So if we write here level a half, we might make a mistake. We do in the sign. More precisely, when we write level a half, the sign is ambiguous. And if we define the sign to be, say, plus for some A, and we vary A, eta will jump in such a way that we'll get the correct answer, and the Chern-Simons term will flip sign and we'll sometimes get the wrong answer. If this is too complicated, just recall what we had yesterday. Yesterday we had the same thing where instead of the Chern-Simons term we just wrote the line integral of A. And there it was clear that the issue was with the 2 pi periodicity. And locally everything was okay, but at some point this eta was discontinuous, and that happened precisely when the Dirac operator had a 0 mode. So this complex number that comes from here and here went through 0. The absolute value emerges with the same sign, with a positive sign, because absolute value is always with a positive sign, but this thing should emerge with a negative sign. The whole issue is about the sign. So you could say that I'm being over pedantic because I pay attention to the sign, but a lot of very interesting physics depends on this crucial minus sign. So what does all this thing mean? What it means is that our Lagrangian I d psi bar d slash psi with A, if we act on it with time reversal, we get the same thing, psi. And again, I'm performing this crime that I'm using form notation for some terms but not for others. So it's time reversal invariant classically, but we have a minus sign in my conventions, minus I over 4 pi ADA. Have we seen such equation before? Yesterday. Yesterday in the quantum mechanics we saw exactly the same story, except that this term was linear in A. So when we perform a time reversal transformation, the action of the Lagrangian are shifted by a term that depends only on on classical fields. The term it is shifted by is well defined. But the normalization is such that we cannot cannot put here 1 over 8 pi, such that we'll have here 1 over 8 pi, and get rid of this term. So there's no way to get rid of this term. I'll say it again because it's very important. We had an ambiguity in the original problem, or ambiguity of freedom, to add such a local counterterm with integer k. That's the freedom we had. We had freedom to add it with integer k. We cannot get rid of this freedom. We cannot use this freedom to get rid of this problem. That's common with anomalies. We have some freedom in how we define the problem. We could say, well, it's time reversal invariant if it might be time reversal invariant if we use the freedom to shift that term. The anomaly is the inability to use that freedom to get rid of the problem. Sorry? I can add k. If I have k here, there will be minus k here. So k will make it even worse. So you could say, well, let's take k equals 0. So we have the problem. So k equals 0 is shifted to be minus 1. So say, let's take k equals 1, but that will shift it to 0. In fact, we could see it already here. It's the same problem that we saw here. There is no way to choose k, which is an integer, such that these two terms form a representation. In this case, it would be ct or t. But we still have a way, yes?
Beforehand, we redefined T such that some miracles happened and things work time inversion invariant.
That was
In the classical problem.
this was in the classical problem when we broke the U1 and we added the mass term. Here, I'm A in the massless theory. B, I do not want to break the U1.
Okay. We were not we were not inversion invariant even before.
So it is true that if we don't want to preserve the U1, I can preserve some time reversal symmetry both classically and quantum mechanically in a massive theory. As a general rule, if you have a symmetry that, I'm glad you raised it, so I'm going to answer a different question, but I think it will be useful. There's a general rule about all these anomalies. If you could turn a master, lift everything, and this will break some of the symmetries, but will preserve a subgroup. That's a very useful thing to do. So step number 1, work very, very carefully to identify the symmetry that is unbroken by the mass term. And we have done that here. And we consider different mass terms. As a rule, whenever you have a symmetry that is preserved by the mass term, if the theory is completely massive, there is not going to be any anomaly. So any symmetry, if you could find a subgroup of the symmetry group which is preserved by a mass term, that subgroup is not going to have any anomaly, because the anomaly is only associated with massless particles. What we did before was to take this theory and classically turn on different mass terms and identify the symmetry that is preserved. Without the mass term, we classically had U1 and C and T. With one mass term, we had the U1 and C but no T. And with the other mass term, we also broke the U1, but we got some kind of a new T. And there was a C, etc., etc. And they had some funny algebra.
So the point here is now.
So that subgroup of the full symmetry group that we could preserve with a mass term is never going to be anomalous. So we could take this system and turn on the U1 preserving mass term that we discussed. It has U1 and C, so that subgroup on its own is not going to be anomalous. We also broke the U1 to fermion number, and we had some kind of a T prime in C. That particular subgroup is also not going to be anomalous. Where can we find anomalies? In that big group, such that when projected to these subgroups, the anomaly should vanish. And here we see the anomaly.
And we cannot redefine T in some way to get rid of
No, you cannot redefine T in some way to do that. You could do that, but then you will break some other symmetry. Yes, because I preserved the U1. You can break the U1. So how can we do that? One way of doing it says, well, let's break the U1. If we don't care about the U1, I can break the U1. Then I can turn on this mass term that breaks the U1 that I discussed before. And then it's guaranteed that there is no anomalies. That's one way of saying it. Another way of saying it, the issue is with his term, which is a background field for the U1. If you don't care about the U1, set the background field to 0, then there's no anomaly. So the mass term is more drastic. It preserves only -1 to the f, or only a Z2 subgroup of the U1. Here, you can actually consider more of the U1 and still have the symmetry. So we had a third option to preserve all the symmetries. What was the third option? Adding the bulk, right. So every 15 minutes I ask this question, and every 15 minutes he gives me the right answer. So we can add a bulk. And what are we going to write in the bulk? Bulk. We need something that would be half of this. So we need I. What we do need to put is I over 8 pi ADA over the boundary. That's what we would like to put. So if we had it here, we could have fixed the problem. But that's not good. So what we do, we will add the bulk and add a D here. Now it's okay. And this can also be written as I theta. There's 2 pi. I probably get the 2 pi's wrong. So there's a pi square, maybe 16. I'm not vouching for the coefficient. And for theta equals pi, it should be the same as that. So it should be 8. Yeah, that's what I need. So this is the standard kind of instanton number. This theta on spin manifold has 2 pi periodicity. But if we set theta equals pi, that's exactly the bulk term we need. So now the boundary theory is not time reversal invariant. The bulk on closed manifold is time reversal invariant. But if there is a boundary, the bulk is not time reversal invariant. And the mistake from the boundary cancels the mistake from the bulk. And then the full z is the absolute value of z. We had this e to the minus ik, k over 4 pi, which we could set to 0 ada. And then there was this term with eta, and there's another contribution from the bulk. And together, they give us just a plus or minus sign, some I. And then we could say, aha, we are going to choose k equals 0. And for k equals 0, this term is absent. The partition function is real, and therefore, it is time reversal invariant. So we can, if we add the bulk, it's still not true that if we add the bulk with theta equals pi, the system is time reversal invariant. That's still not accurate. What is accurate is that we have a choice of k such that the system is time reversal invariant. So we really need to use, wherever we had freedom, we have to use that freedom to achieve that statement. Now, somebody else might have a different regularization scheme. It all depends on how we regularize things. So somebody else might have a different regularization scheme. And it's a general rule that different regularization schemes differ by adding a local counter term. So Talia and I will have different regularization schemes. Both of them are correct. There's no preferred one. And there will be a dictionary between her regularization scheme and mine. The difference, the dictionary will be that what I call k equals 0, for her it will be k equals 7. And what I call k equals minus 7, for her will be k equals 0. So we'll have to take all these things into account, including the choice of k to achieve this time reversal symmetry. Now imagine we turn on the mass, the U1 invariant mass. When we turn on the U1 invariant mass, this problem should go away. So what we're going to get is with the mass, what am I going to do? So with the mass, the partition function has a phase, which is e to the I, say minus 1 plus the sine of m, sine. Some people write sine without an I. I can never remember which one is right. ADA. So the half, which was imprecise, was there before from eta. And the sine of m, which is also imprecise, come from integrating out the fermions. But together they give us something well-defined. And there's an integral. So if we give in positive mass, so these two terms cancel, and we say k of the low energy theory is 0. I think I want the other prescription. I'll put it 1. Is 1. And if m is negative, k of the low energy theory is 0. So if I vary m, this is the U1 invariant mass. For m equals 0, we have the massless theory. And here, we have 0 over 4 pi ADA. Sorry, 1 over 4 pi ADA. And here we have 0 over 4 pi ADA. And if we started with a bare k, here we are going to have k plus 1. And here we are going to have k. Indeed, the same thing is true in this quantum mechanical system. When we turn on the mass, either this is the ground state or this is the ground state, because the mass term splits them. And which is the ground state depends on the sign of the mass. So we are going to refer to this as U1 level k plus a half. What does this mean? I will take this label here to be the average of the level here and the level here. This could be half integer, because this does not mean that there is a half integer coefficient in front of the Chern-Simons term in the Lagrangian. That doesn't make sense. What does make sense is there's a bare k, which is an integer, which sits both here and here. And there's this whole business with eta, which would not be thought of as half integer u1, half integer level, in such a way that when we give a mass, the system is gapped, the coefficient has to be an integer. So this is an integer, and this is an integer, and what I put here is the average between them, such that it will be independent of choices. How much time do I still have? Okay, I still have plenty. At m, so this is the low energy effective Lagrangian, or if you wish, this is the classical background Lagrangian. So we integrate out the massive fields, and we find that low energy is this Lagrangian. And if we are in Euclidean signature, put an I. Right? So this is the effective L, which depends only on the classical background fields because the system is gapped. The system is gapped, A is classical, and what the low energy observer sees is only this term, and also here. In between, the system is not gapped. In between, the fermions are massless. In between, I mean at the transition point, the fermion is massless, and therefore I cannot write any Chern-Simons term. It's much more complicated. The effective Lagrangian is non-local. If I look at the partition function, it's a non-local functional of A. It's even meaningless to ask what's the effective Lagrangian for A at low energies, because it's non-local. But for positive and negative mass, it is local, and that's what it is. And you see from here, the time reversal should reverse the picture, change the sign of M, and there's no choice of K that this will be mapped to that under time reversal. So we have, as we said, I would like to repeat again the options we have. Option 1 is have this and just live with it. Option 2, add the bulk. The bulk will allow us to effectively shift K to be half integer, but then we provide more data, what A does in the bulk. There's another option to say that, the fermion really has charge 2, not charge 1. And I'd like to say a few more words about that. Recall again, A is classical, but I have in mind making A a dynamical field. And when I make A a dynamical field, I will not have the option of adding the bulk, because I would like to keep the system three-dimensional. So as long as A is classical, perhaps the best option is to add the bulk, and things depend on a little bit more information, but that's life. But if A is dynamical, I don't have the option to add the bulk, because dynamical fields live only in 3 dimensions. It's only this background field that I added from the outside that could live in the bulk. In this case, if A is dynamical, T is actually broken. It's not just an anomaly, but there's no T symmetry. But imagine we write it with the coefficient with this 2. So I have psi bar d slash I. And instead of A, I write 2B. So B is a properly normalized gauge field. And I use the letter B because it's actually everything I said so far with A can also be repeated with the spin C connection. And then A is a spin C connection, and we don't even need the choice of spin structure. If you didn't follow the last sentence, ignore it. If I put a 2 here, I violate the spin charge relation, because now psi has charge 2, and it has spin a half is better. Has spin a half, so it doesn't satisfy this selection rule between spin and charge. So this system cannot be put on a spin C manifold, but it can be put on an ordinary spin manifold. So it's U1 with charge 2. The anomaly would tell us that on the time reversal, so T of this is the same thing, plus, and I don't even care, not even pay attention to the sign. So we're going to have I in Euclidean space over 4 pi, 2b, d, 2b. But now I can say, now I can use the freedom with k to fix the problem. Now I can fix the problem with k by adding here 2 over 4 pi bdb. So that would give us minus 4, and I think I got it right. So if I add this counter term, the system is time reversal invariant. So the U1 problem, the problem with the free fermion, coupled to background field with charge 2, is not time reversal invariant, but it can be made time reversal invariant by adding this local counter term. So time reversal will flip the sign here, which will exactly cancel the mistake, the anomaly in time reversal. So with charge 1, we cannot do that. With charge 2, we can fix the problem. What about charge 3? Sorry? No. What about charge 4? Yes. So with even, sorry?
Even charges we can.
Even charges, we can fix the problem. With odd charges, we cannot fix the problem, and I'll leave the arithmetic to you as an exercise. You will soon see deep consequences of this result, this statement. This is all I wanted to say about free fermions. Everything I've said in all my lectures until now was fully understood by the 70s or maybe mid-80s. I don't deserve any credit for anything I said so far. It was all fully understood then, and I think after talking here for 2.5 lectures, I deserve to move to the 21st century. And before I do that, are there any questions?
So, looking at the low energy sector essentially corresponds to looking at the lowest lying Landau levels on the sphere. So I was wondering what are some of the condensed matter implications of what you have discussed so far?
Oh, the condensed matter implications of this theory are really enormous. It's visible in the quantum Hall effect, in the fractional Hall effect. It's visible in SPT phases. I deliberately did not tune these lectures to condensed matter audience, although I understand that there are some people here who are nominally condensed matter people, but I understand that their fraction in the audience is small. A few years ago, I gave essentially the same talks, pitched a little bit differently, to a similar school here, which was mostly condensed matter, and that's also online, and that's pitched completely differently. There I emphasize more the condensed matter implications. And in any event, I'm not an expert in condensed matter physics.
Can you motivate us? Why should we keep the time reversal invariance? What's so good about it?
Well, it's a symmetry. If you have an option to preserve a symmetry, you should better do it. Now, you might be interested in a situation where you don't preserve the symmetry. That might happen. If you have an experimental system and it has a symmetry, you would like your formalism that describes it to have the same symmetry. Now, it's often the case that just by thinking of the symmetries and their anomalies, you can learn quite a lot about the system. And since these systems are very complicated, it's very hard to analyze them. The anomaly, the symmetry gives you a very powerful tool, and not paying attention to it would be a mistake. Like, imagine you want to compute the volume of a sphere. So this problem has rotational symmetry. But you say, no, I love Cartesian coordinates. I'll do the integral with Cartesian coordinates. You can do that. There's nothing wrong with that. But then your question would be, what's so good about rotation symmetry? Well, I shouldn't even continue this discussion. I hope the point was well taken. So if you have a symmetry in the problem, it's usually a good idea to try to preserve it. And if actually the more subtle symmetries, like the fact that we saw that C and T don't commute in that mass term, that actually has surprising implications. Because if the symmetry is subtle, the implications will be subtle. And depending on how fast I go, I might show a system that actually demonstrates these subtleties in a very interesting and powerful way. We'll have exactly the same system. Every simple example that I mentioned here, I have an application for later.
Also, we changed the time reversal operator and things like that. Does it have any implication on the actual
Yes.
time of the system?
Yes. So All of them reverse time of the system. There's always a question. The ambiguity in a time reversal transformation, remember this was Talia's time reversal and my time reversal. Both of them were good because they differed by a unitary transformation that commutes with the Lorentz group. So we have all the set of all unitary transformations that commute with the Lorentz group. That's a subgroup because we impose conditions. What do we mean by time reversal? Well, we have freedom because it's anti-unitary, which does not commute with the Lorentz group. But that doesn't uniquely define it because we can always attach to it a unitary transformation that commutes with the Lorentz group, and its defining property will remain. Now, it's very important to see, so you pick one time reversal symmetry, that's what we did in the example, and we realize that it's not the symmetry of the Lagrangian. It would be wrong to conclude, therefore, the system does not have any time reversal symmetry. Why? Because there could be a combination of your choice of T with something else that is broken, so that together it's unbroken. And it's absolutely essential to identify correctly the full unbroken symmetry.
So this corresponds to some coordinate summation of time itself?
No, time goes to minus time on the time reversal. It's the difference between them is what we do on other fields. The quantum Hall effect, as it stands, does not, because it has magnetic field. No, it does not have. Does not have it. Because you put the system in a magnetic field, it's obvious that there is no time reversal. There might be CT, but there is no T. Now, in condensed matter physics, what we call CT in condensed matter physics is called particle-Hall symmetry. Are you from condensed matter background or no? So there's huge discussion on that, and sometimes the symmetry is not there microscopically, but it becomes a symmetry at long distances. It could be emergent symmetries. So yeah, this is a long story, and it should be discussed on a case-by-case basis. And I present here a few characteristic examples, hoping that they highlight some of the things that appear in more subtle examples. In fact, the next thing I'm going to talk about will have such an emergent symmetry at long distances. It would not be a symmetry of the Lagrangian, but a symmetry at long distances. I'm really behind schedule, so I have two options. Go slower and make sure that people understand. Go faster and cover more material. Or go in between and make sure that I both lose people and don't cover what I want. It's a combination of the two.
You said that it is not reserved when you have the magnetic field, but CT is?
Yeah.
But you can think of it the opposite way, right?
Well, I use my conventions.
Okay.
You would say T is preserved and CT is not. One of the two is preserved and the other is not. So I'll stick to my conventions because this thing is so confusing. Everything is about minus signs. So you could say, oh, I work up to a minus sign. That's really, you haven't done anything if you work up to a minus sign. Everything is about the minus signs. And there are conventions of what you mean by T and what you mean by CT. And there's convention of what the signature of space-time is, both whether we are Euclidean or Lorentzian, or whether the metric is mostly plus or mostly minus. Now, lots of minus signs, lots of places to make mistakes, and I try to be either consistent throughout the talks or tell you when I switch conventions. Because sometimes there's one convention is more important than the other. And in addition, when I do it, I also make sign mistakes when I do calculations. So yeah, it's painful, but it's really worth getting it straight because this has really deep and very profound implications.
Would you say that in fundamental formalism of physics, you can always find this time reversal?
No, it's not true in nature.
Well,
Nature doesn't have time reversal symmetry.
I know
The case system shows that nature does not have time reversal
Yes,
symmetry.
of course.
And there's no way to redefine time reversal, such that it does have it. That's very important. Nature does not have time reversal symmetry.
Obviously, nature does not have this. In the level of fundamental physics of Lagrangians and particles, it's also not true?
The standard model of particle physics does not have time reversal symmetry. Now, if all you're interested is chemistry, then the effect of time reversal violation is very small. But it is measured. It's measured. Even in atomic physics, people measure the effects of time reversal violation. In fact, the best measurements of time reversal violation actually come from atomic physics. But these are tiny effects which can, even though they're tiny, they can be measured very accurately.
When you say in nature there's no time reversal invariance, do you have CP violation in mind, or is there some?
Well, if it's relativistic, T is the same as CP. And the mnemonic to help you remember is that CPT is a rotation in Euclidean signature. And if you want to have the Lorentz symmetry, then you must have CPT. Okay, am I allowed to continue? Okay, so now we're going to put all the elements from the 70s and the 80s that we laid in place. And in the rest of my talks, we discuss the 21st century. And we'll put them together to show how this particle-vortex duality in a bosonic system that I discussed in the first problem, which was in the discovered in the late 70s, when I was more or less your age. Then it was discovered. And we are going to dress it up now with fermions and Chern-Simons terms and so forth, and discuss some more modern developments. So let me recall what we had. We summarized the discussion by writing it this way. Square plus pi square dB hat phi hat square plus phi hat to the fourth plus I over 2 pi b hat dB. And let me remind you what every piece here means. First of all, the notation, we are in Euclidean signature. Second, on the right-hand side, I mix notation. Here I use form notation. So this is just integral of this. The action is just an integral of this. And these two terms are not in form notation, which means that I have to multiply that by d3x before I integrate. So I use this somewhat imprecise notation to save writing. Second, this is shorthand for writing a Lagrangian with phi to the fourth and phi square and flowing to the infrared and adjusting the coefficients such that we hit a second order point, and then describe only the low energy physics. So the left-hand side is shorthand for this long story. It's really starting at short distances from phi to the fourth theory with its coefficients. It has a second order point. We adjust the mass term to the second order point. The phi to the fourth coupling went away because we've done the flow and we are at low energies. Similarly here, we adjusted one coefficient. We were in some range of parameters in the coefficients of phi square in the gauge coupling. This was the gauged O2 model. And we also find the second order point. And the non-trivial statement is that these two theories are the same CFT. So we discussed that in the first lecture. And now I'm going to modify that. I'm going to add to both sides of the duality so I'm throwing in another gauge field, A, which to be precise is a spin C connection such that this combination makes sense. If you don't like that, this is just another U1 gauge field. So I do that on both sides of the duality. Phi is quantum, B is classical, and A is classical. Recall my conventions that all uppercase characters are classical and all lowercase are dynamical. I obviously have not changed anything. I just added classical fields with some terms. The duality is still valid. Now I'm going to perform functional integral over B. How do I perform functional integral over B? That's easy. I just change it to lowercase in this notation. So I'll do that here. So this will be a little b, this will be a little b, and this will be a little b, and this will be a little b. And we do the same thing on the left-hand side. Now it's not so obvious that the two sides are the same. Because if we go to low energies, we are at the fixed point. There is a global U1 symmetry. We can weakly gauge it. This is still correct. And we do that. But if we look at the right-hand side, say, we had to tune some gauge coupling and some coefficient of phi square to be at the points where there's a second-order transition rather than a first-order transition. And also we had to tune to the critical point. When we do that, there's also the gauge coupling of little b. So we have more parameters to adjust. So the only assumption I'm going to make is that this duality is still valid, and at long distances, I can find a range of parameters such that there is a second order point both on the left and on the right. With this assumption, I'm guaranteed that the second order point is the same. Because I started from the range of parameters that I just had a fixed one conformal field theory. It had a global U1 symmetry with coupled to big B. That was in lecture 1. It was not 100% proven, but it's with very high confidence this is true. And now we had a functional integral over B, we just do it. So we get a new duality. Now let me manipulate both the left-hand side and the right-hand side. And we're going to use all the Chern-Simons technology that we learned before. So on the left-hand side, what do we see? This is the gauge O2 model with U1 level 1, coupled to a background field. So this is the Wilson-Fisher theory, coupled one level 1. This is not a trivial theory because the gauge field of this U1 level 1 couples to phi. So it has some dynamics. It's the O2 dynamics and the dynamics of this little b with U1 level 1. What do we have on the right-hand side? On the right-hand side, the b appears only here and here and here. So I can complete the square. So I can write it as I over 4 pi b plus b hat plus a d b plus b hat plus a minus I over 4 pi b hat plus a d b hat plus a. So I've rewritten all these terms. Yes, I even got it right. So now I can redefine what I mean by b by shifting it by these two, because b appears nowhere else. So this part of the Lagrangian is really a decoupled U1 level 1, which we discussed at length. We can integrate it out. It leads only to a gravitational Chern-Simons term. But since I'm ignoring the gravitational Chern-Simons term, I can just erase it. So let me collect all the terms that we have on the right-hand side. So on the right-hand side, so here we had this. What do we have here? We have d b hat phi square plus phi absolute value to the 4th. And this, and this are replaced by these, which is minus I over 4 pi b hat db hat minus I over 2 pi b hat dA. I've integrated by parts, minus I over 4 pi ADA. This is very much like the left-hand side. What is it? This thing is the Wilson-Fisher theory coupled to U1 level minus 1. You see there's a minus sign here and a plus sign here. So the sign was reversed. And coupled to the same A on both sides. And another counter term. So let's first set the background field A to 0. Let's set first the background field to 0. What do we learn? We learn that the same Wilson-Fisher theory coupled to a gauge field with U1 level 1 is the same as the same Wilson-Fisher theory coupled to a U1 gauge field with level -1. This is extremely surprising because the left-hand side is not time reversal invariant. You know, it has an epsilon tensor here and here. And yet, the duality tells us that it's the same as the result after time reversal. So the claim is that the Wilson-Fisher theory with U1 level 1 is not time reversal invariant. That's obvious. But it flows at long distances to a time reversal invariant fixed point. We'll soon identify the theory at the fixed point. But that by itself is surprising because it means that the theory has an emergent time reversal symmetry. Somebody asked me here before, I think you, about some symmetries that can appear at long distances. Here the claim is that we should start at short distances with a system that is not time reversal invariant. And that system, which does not have this time reversal symmetry, flows at long distances to a fixed point, which does have time reversal symmetry. How does time reversal symmetry work? Well, in the UV, it's not a symmetry. So I could say it will pick your choice how it works. It's not going to be a symmetry. At long distances, what it does, it maps this phi to this phi hat. And I left out the hats here. So roughly, T of phi is phi hat. And T of B is B hat. So time reversal acts non-locally at short distances. This new emergent time reversal symmetry, and it becomes a symmetry at long distance in the long distance theory. So I can be a little bit more precise. I continue to use my conventions. The T of A is minus A. And if we just follow the signs here, I would say that T of phi is phi hat, and T of B is minus B hat. I would like to write the action of time reversal in the IR in a better way. Our Lagrangian is the left-hand side. So let L be, so the T of dB phi square plus phi value to the fourth plus I over 4 pi B dB plus the coupling to the background field I over 2 pi B dA. I wish I had Douglas's beautiful handwriting. Is dB phi square plus phi to the fourth minus I over 4 pi B dB minus I over 2 pi B dA. Right, I just acted with time reversal in an obvious way. Here. I just reversed the orientation. And using the duality, this is the same as dB phi, dB hat, if you wish, phi, absolute value square, how did I write it? Plus phi, absolute value hat to the fourth, plus I over 4 pi B hat dB hat, plus I over 4 pi B hat dB hat. So this is the same as the original Lagrangian, plus I over 4 pi ADA. That's very interesting. The system at long distances. BDA, thank you. Now I know that when Offer corrects something n, and it's 1 over 2 pi, yeah. When Offer corrects me, he's always right. Sorry? Okay, so let's do it in steps. Maybe I was too fast. Time reversal flips the sign here and here. That's here. Now I'm going to the duality. I'm using the duality. The signs are flipped back because this is dual to that. So I shouldn't even write equal sign. I should write dual to. I flipped the signs using the duality and added this term. And then I realized that this term is the same as that. So what do we learn? That for a equals 0, the system is time reversal invariant. That was the first surprise, that at long distances we have a symmetry that we didn't have before. But it's not quite right, because when we turn on this background field, it's shifted. Have we seen that before? Yeah. How many times have we seen it already?
Twice.
Twice? I think more than that.
Yeah, at least twice.
At least twice. This is an anomaly. The system has an emergent time reversal symmetry with an anomaly. In fact, if time reversal symmetry was an exact symmetry at short distances, and everything at short distances was kind of classically time reversal invariant, there wouldn't be any anomaly. But since the symmetry is emergent, it wasn't there at short distances, it's surprising that it emerges, and we shouldn't be that shocked that it emerged with an anomaly. So this is a very interesting fixed point. This fixed point has time reversal symmetry with an anomaly. And we've seen such a fixed point before. This was the free fermion theory. The free fermion theory has time reversal symmetry with an anomaly. It couples to such a spin C connection A. And I think I need an I here, ADA. And in fact, I'm going to argue that this theory is a free fermion in disguise. But before I argue that, let's analyze the system in more detail. What are the operators in the theory? Let's map the operators across the duality. One operator we can easily map is phi square. It was mapped already when we started with the Wilson-Fisher theory, and it was mapped to minus psi hat square. Remember, the Higgs phase was mapped to the broken phase, and the unbroken phase was mapped to the un-Higgs phase. And we mapped the global symmetries and all that. Now these global symmetries are gauged, but the map of coefficients is still right. This term is surprising because in the original problem, it was time reversal even. Now we broke time reversal, the naive, the UV time reversal, we broke it explicitly by the terms that we added. And if I just look at the infrared, I told you that time reversal maps phi to phi hat, maps these degrees of freedom to these degrees of freedom. And therefore we see that this operator is time reversal odd under the emergent time reversal symmetry. And we can check what happens to the theory as we turn it on. We'll soon do that. Before I do that, I would like to map another operator. This theory has monopole operators. So let's start from the left-hand side. It has monopole operators. So I move a point from space-time. I'm surrounded by a sphere. The nice thing about this set of lectures is that we get to do everything many, many times. And eventually I get it. So we take a point, we put an S2 around it, and we specify boundary conditions that the integral of the gauge field, on the left-hand side it's B, is 2 pi. So we define a monopole operator, M sub B. Now, we look at this term in the Lagrangian, and if we have integral of B, dB is non-trivial, we see from here that it carries charge 1 under the U1 gauge symmetry. So this operator is not gauge invariant. It carries charge 1. How do we make it gauge invariant? We write phi dagger MB. So let me just make sure I have my convention straight. Yep. So we consider this thing. So this object is gauge invariant. But it has interesting properties. First of all, we have a magnetic monopole. This is a classical configuration. And this is a charge 1 boson. And we have discussed before what happens when you take a charged particle in the background of a magnetic field. And I gave the reference to Dirac. It has some spin that it has because it has spin. The background has spin 0. The particle, in this case, has spin 0. Before we had spin 1/2. And there's another contribution to the angular momentum coming from the electric charge times the magnetic charge over 2. In this case, it gives a spin 1/2. So this is an object with spin 1/2. Furthermore, I look at this coupling in the Lagrangian and I integrate B by parts. I see that it has charge 1 under A. It has spin 1/2 and charge 1, the U1 of the classical field A. So I'm going to denote this operator by psi. It's an operator of spin 1/2, and it carries charge 1 under U1A. I would like to emphasize that this is true even in the UV, independent of what we find in the IR, independent of whether it flows to the fixed point or not, there is an emergent time reversal symmetry or not, it's dual to something else or not. I just analyzed this Lagrangian with all the terms that I have to add in the UV. There is such a monopole operator. It has spin 1/2 and charge 1. What happens on the right-hand side? On the right-hand side of the duality, I'm going to consider a monopole for B hat. So I have an M of B hat. And here I need to multiply it by phi hat. It has charge -1. But this is still true, and this is still true. And I'm going to identify these two objects. Actually, to be consistent with my conventions, I'll put daggers on both. So we have a fermion operator, which is phi dagger, the monopole of B, and it's dual to phi dagger MB hat dagger. So both sides of the duality both sides have an operator of spin 1/2 and charge 1. That's good because it's a consistency check of the duality. Now let's go back to the deformations. And an interesting deformation is this mass deformation of the boson. And without loss of generality, I'll analyze it on one side, and then we'll analyze, it will be straightforward to analyze it in the other side. So let's deform in the left-hand side by adding plus phi absolute value square on the left-hand side. So what does it do to phi? If I add phi square with a positive sign, what does it do to phi? That's not the right answer. What does it do to phi? To the particle phi. It gives it a mass. That's a mass term for phi. So phi is massive, and I can forget about it because it's heavy. And I'm left with, so I'm adding this, so I'm left with U1 level 1, so BdB plus that. So I have I over 4 pi, BdB plus I over 2 pi BdA. I complete the square because it's U1 level 1, and I find minus I over 4 pi AdA. So the spectrum is gapped, and what we see at low energies is minus I over 4 pi AdA for the background field. Let's do it on the other side, and I claim we need to put it with the minus sign. I can't manage these blackboards. So left-hand side is this duality I wrote here. That comes with a minus sign, so it Higgses B hat. So on the other side of the duality, we have minus phi hat square. Since it has a minus sign, it's the Higgs phenomenon. It gives a vev to phi, and it Higgses B hat. So I don't have to think about B hat. It's gone. And I have the same thing, minus I over 4 pi ADA. Let's do the other sign. With the other sign, so we have Higgsing on one side and giving mass on the other side. Now let's do the other sign. There's a check. So we have minus phi absolute value square. What does it do on the left-hand side? We have negative mass square. What does it do? It Higgses it. Very good. So it Higgses B. So B is gone. B is gone, and I have nothing. And the spectrum is gapped, and there is no term that depends on A. What happens on the right-hand side? On the right-hand side, we should bring it with a plus sign. What did you say?
Becomes massive.
You give it becomes massive. Very good. So it becomes massive, and what I'm left with at low energies is, so this is massive. I'm left with B hat and B, and the coupling to A, and so this is 0. And I'll leave it as an exercise for you to show that they combine to a perfect square, and we get 0. So what do we see? We have this putative fixed point, and as we vary phi square, so let's call it R, for R positive, so R, for R positive, so the system is always gapped when we turn on either positive or negative R. Here, for R positive, we have minus I over 4 pi ADA on either side of the duality, and for R negative, we have 0. What's the spectrum of the particle? I have 2 minutes, so I'll just state the answer. The spectrum of the particle in these two phases is easily analyzed. For one sign, phi is massive. We have these phi particles. They are not gauge invariants, they are attached to B's. And if you go through the arithmetic, the spectrum is a massive, spin a half, so it's a fermion particle, with charge 1. And I leave it as an exercise for you to show that this is true on the two sides of the duality. On the two sides of the duality for the two different values of R. These are 4 computations. We should do R positive and R negative separately on the left-hand side of the duality and on the right-hand side of the duality. And either way, we find the same answer, that the spectrum has one massive spin a half particle with charge 1. So let's summarize what we know about this theory. We have 2 different bosonic theories that flow to the same fixed point. That fixed point has time reversal symmetry with an anomaly. It has a relevant deformation that we checked on both sides of the duality, that with one sign, so it gaps the system, and with one sign, we end up with minus I over 4 pi ADA. With the other sign, we end up with 0. And the spectrum on both sides has fermion, one fermion particle, with spin a half. More precisely, it's 1/2 at one side and minus a half on the other side. Again, operators in 3 dimensions are in representations of SU2. Particles are in representations of U1. So in one case it's spin a half, in the other case it's spin minus a half. Is this familiar? Are we familiar with such a fixed point? A fixed point where there is a fermionic operator, psi, with charge 1, and with a deformation that gaps it, that breaks time reversal symmetry. It has time reversal symmetry. The deformation breaks time reversal symmetry and gives us a massive particle, fermion, with spin plus a half for one sign and minus a half for the other sign, and this time reversal symmetry is anomalous. This is the free fermion. So this system is really a free fermion in disguise. Or this is a bosonic system, which at long distances becomes a free fermion. In the next lecture, we'll analyze it in a lot more detail, this boson-fermion duality, and we'll put it to use and we'll see some applications of it. I'm near the end of I'm in the middle of my second lecture now, according to my plan, but I think it's better to go slower. So if you want me to slow even further, I'll be happy to do that. If you have questions, we have a tutorial today. Feel free to come and grab me in the corridor, and I'll try to be helpful. I'm not always successful in that, but at least I'll try. Thank you.
הסיפור עם האנגולר מומנטום במונופול זה לא שהוא נמצא